So I'm going to use these graphs here to help explain random and systematic error. The red is the true value or the actual value, and what you normally have happen when you use various instruments or readings is some points will be higher and some points will be lower, and so that is random error. So above or below the true value, usually due to limitations of equipment. Systematic error is far more important. Now there's always random error even with a systematic error. You can see there's a little bit below and above, but random error is quite normal and always present. Systematic error is the one you want to mention if that is unique, and just ignore that there's random error as well. And so if you're getting values that are always too high or always too low, or they're sort of close but then they're sort of getting more and more apart, that's a systematic error. So in one direction, usually due to instrument or method error. And so you'll mention that that's a systematic error and then try and work out why that is the case. Now, just to emphasize, because most textbooks are not clear on this, systematic error is always the one you talk about if it exists. Random error always exists because there's uncertainty on the instrument and there's other factors going on in the experiment. So there's always random error even when you think something quite solid as this, like there's a missing increment on the burette, so it just jumps in readings, and so you know for sure there's 1 mil. But that will still have an error, as will every other known set value for systematic error. Most systematic errors have quite a large random error as well, such as loss of magnesium oxide when you're doing empirical formula experiments, or when you're doing, say down here as well, when you're doing burning, you're doing calorimetry. And so they have quite large random errors as well, but you just ignore that because you will write that out, but that's not the point. The point is the systematic error tells you that there's a method problem. And so most textbooks are really quite poor on telling you what random and systematic error is. I had a 40-year IB examiner said that they would go to Damgee and Green as the authority, and Damgee and Green does actually list quite clearly. Systematic error can lead to a result being inaccurate, and if it's variable, like has a large random error, it can also be inconsistent. So it says it here that there is also, most familiar systematic error is heat exchange to the surroundings. That has a huge random error, and here it's talked about random error within a systematic error. Okay, so systematic error, always talk about it. Random error always exists. Don't call something a random error if it's a systematic error that has random error. Just call it a systematic error. Just to take it one step further also, if you really want to get advanced on what's acceptable and what's not, go look up the Westgard rules. This is more for biology because they use standard deviation and huge data sets that you might not be able to understand easily. And so they count up the number of standard deviations above or below here to determine and the degree, whether it's 1, 2, or 3 standard deviations. This one here is the one I want to just let you know that it's not just above or below. A systematic error can make it trend upwards or trend downwards if there's something wrong with the method to cause that. So that systematic error could actually be better defined in Damgee and Green. They could also include the fact that there's something that's getting continually worse or continually better as the experiment goes forward. So a trend is also a systematic error. When you look at accuracy and precision, they're closely related. And so accuracy is closely related to having no systematic error, and precision is closely related to having very small random error. These ones here, so this is quite precise, has a very low uncertainty, and it averages out quite badly off the mark here, so it's a low accuracy. If you average out this one here, it is highly accurate, but there is low precision because the uncertainty is quite large. Whereas here, the accuracy still averages out to the right value, but the precision is much higher, the uncertainty is much lower. So precision is a measure of how uncertain it is, how largely the values are up and down around the true value, and the accuracy is the true value. And so just be aware of using the terms correctly. Just to finish it off, reliability means that with the method you can repeat and get the same values again and again. Whereas validity is the test is actually testing for what you say it is and not for some other independent or dependent variable, which is quite common Just have to interject and add one more slide in here, sorry. You just got to realize that it's biology that really worries about things that are invalid, because they have studies like this. They just can't control their variables. And so if they're trying to say that caffeine increases or decreases your energy, you look at this study and it's just, it could be novelty effect. They just, as the study goes in, this is interesting, and so therefore there's more energy and attention given to it. It could be just because they're progressing through the day and that's why they're naturally just waking up. And it could be the energy is due to glucose or milk in the coffee. That's not actually got anything to do with the caffeine. And so this is why the words reliability and validity are such big issues for biology and not for chem or physics. In biology, these two, which is why QCA has done a one-size-fits-all and sort of said accuracy is equal to validity and precision is equal to reliability. Don't do that. Just make sure you clearly understand the definitions of these four words and use them in the correct place. QCA has gotten a little bit too loose with the term, so it's even gone to the point where they've said accuracy is equal to precision. And so don't do that. Just use the terms correctly, understand what the definitions are, and use the correct one of those: accuracy, reliability, validity, and precision in the right places. Okay? So what is the ideal data range and repetition? Well, usually the range of 3 doesn't let you know whether it's linear or reaching a maximum or increasing or decreasing rate. So usually 5 will help sort that out if you extend the range. The repetition, because chemistry and physics are hard sciences where everything's tightly controlled, such as a titration, you can get away with 2. We normally do 3 just to be safe, or maybe 2 with a rough. Generally, because we're doing absolute uncertainty, the mean, which is a statistic, we've now gone to 5, so repetition of 5. What's the true answer? Well, the true answer is you take a cumulative average, and so for biology it often ends up to be around 10, but it can be more. So once taking more values doesn't change your average within your predetermined acceptable uncertainty limits, that's how you actually know what the true number of repetitions you should be taking. Okay?